Hello everyone, thank you for watching this video. My name is Wei Chen. I'm in the Department of Supply Chain Management at Rutgers University. With me today is Dr. Siyang Gao from City University of Hong Kong. Today we are going to introduce a paper we recently published at the Palm Journal titled Optimizing Resource Allocation in Service Systems via Simulation, a Bayesian formulation. As we know, many service systems do not have trackable mathematical structures due to its operational complexity, process nonlinearity, and performance variability. So, to evaluate and optimize such systems, we typically rely on using simulation models. The picture here shows an example of emergency department in Hong Kong. In this paper, we focus on using simulation-based optimization techniques in solving a class of problems where service objective and constraints are probabilistic measures. Take this ED example. They categorize patients based on their urgency levels into multiple categories, and they impose pretty high service level requirements on urgent patients. For example, category 2 patients, 95% of them has to be treated within 15 minutes. However, they realize that their service levels on less urgent patients can be further improved by properly managing and reallocating the resources available to them. If we write these constraints into mathematical formulations, they can be expressed in such chance constraints or probabilistic constraints. And the objective is to optimize or maximize the less urgent patients' service levels. Here are some highlights of the paper. First of all, when using simulation-based optimization in selecting the best design of the system, we often focus on maximizing the probability of selecting the best one. However, service providers typically are more concerned with the loss incurred in selecting a solution. Therefore, we propose a constraint ranking and selection formulation with the objective of minimizing the expected opportunity cost of the selected solution. Second, the performance of neighboring resource allocation scenarios may be correlated, and the modeler may have already obtained prior knowledge on their joint distribution. In order to capture such information, we use a Bayesian model in this paper. Finally, the objective and multiple constraints are stochastic in nature and in the form of probabilistic measures. This enables a convenient asymptotic analysis on rate of decay of a Bayesian EOC and a strong convergence analysis of the resulting iterative algorithm.
Hello, this is Yang Gao, another co-author of this paper. Next, I'm going to talk about the algorithm and the managerial implication of this research. Based on the ranking selection model built in the previous page, we can solve it and find the asymptotically optimal sampling scheme of this problem. So this sampling scheme can help us select the optimal resource allocation scenario. Next, we'll design an algorithm that can sequentially realize this optimal sampling scheme. So in the beginning, this algorithm allocates an equal number of simulation samples to all the candidate resource allocation scenarios. Next, in each iteration, we are going to provide a small incremental sample budget and allocate it to some scenario that can move the current sample location to the optimal sample location as much as possible. We keep doing it until our sample budget is used up. After sample budget is used up, based on the sample means, we will output the estimated optimal resource allocation scenario. So, to summarize, the proposed model and algorithm can effectively solve the resource allocation problem considered in this research. Since we incorporate a correlated prior for resource allocation scenarios that are similar to each other, our algorithm will be particularly efficient for problems with a large solution space. We have applied our algorithm to a staff allocation problem in an emergency department. The numerical result shows that our proposed algorithm is much more efficient than the state-of-the-art algorithms. At last, we would like to thank the editorial team of this paper, including the department editor, Professor Mike Panido, the anonymous senior editor, and the 2 anonymous reviewers. They have provided very valuable comments during the review process. In addition, we also want to thank the funding agencies of this research, the National Natural Science Foundation of China and the City University of Hong Kong.